With that, I welcome Christian to talk about the emerging quantum materials and technologies.
Thank you very much, Jeremy, and even thank you for having me here. It's really my pleasure to be here. Beautiful campus. I've never been in this building for certainty, so it's nice to be here. Nice day, and of course I like that turnout, and I like to thank Sigma Psi for making this happen. So I like to talk about these emergent quantum materials and quantum technologies. And of course, before we dive into this, that there need to be a few words about what is that actually we are talking about, and why would anyone care about this, right? And I try to make this point. So this is a science cafe. I try to be, let's say, understandable as good as possible. So let me first start with a brief outline of what I'm trying to get achieved here today. First, I will briefly introduce the center Jeremy just talked about, the Nebraska EPSCoR Center for Emergent Quantum Materials and Technologies, and give you a little bit of background we have at the campus in Lincoln in terms of nanoscience and nanotechnology there. And then I switch a little bit and go really start from scratch. If you like, anyone has seen the Big Bang show where Sheldon teaches Penny physics, and he starts with the ancient Greek. That's this chapter, just way before the ancient Greek. So I want to make the case between material science and technology really much in general, and how we pretty much go from the Stone Age to today's quantum materials. And then, because quantum materials and quantum technologies, basically that falls into the category of what we call now the second quantum revolution. And it's not always clear what the second quantum revolution is. We better first understand the first quantum revolution and then contrast it to what is new and what we are interested in today in the second quantum revolution. So I give a brief introduction again to the first quantum revolution, particularly looking at it from the perspective of condensed matter physics, and also make the case that a large amount of the highest technology we have today basically originates from the fundamental achievements of the first quantum revolution. And then I go to the second quantum revolution, which is what this center is actually about. And I contrast these two things, and then I go into some more details what we do in this field. This is, of course, a research enterprise that is taking place all over the world right now. It's really a hot topic, but I tell you what we do and how we plan to contribute and hopefully move the needle a bit with this center. And then I summarize and conclude. Okay, so let me briefly introduce the center, and I want to first point out how this came to this point, so you can, if you like, reference Isaac Newton's famous saying that if I could see further, then it's because I'm on the shoulder of giants, and those giants at UNL, where I would argue these centers we have for decades, the Nebraska Center for Materials and Nanoscience, which I'm now honored to be the director of it. It's a big center. It has 100 what we call NCNM faculty and 20 million of annual research expenditures. And an outgrowth of this center is a smaller one, an NSF-funded center called Nebraska Nanoscale Facility. And this is a center which got renewed, I think, 2 years ago. And it is a 3.5 million center NSF grant that we got. And that helps us out a lot in addition. So we have a rich, what I want to say here, we have a rich tradition at UNL in nanoscience and nanomaterials. And we can build on that. In particular, we can utilize our core facilities. In addition to that, we had 18 years of NSF-funded materials research, science and engineering centers under different names, but always these MERSECs. If you know those MERSECs, they are very prestigious, hard to get NSF centers, and we were happy in Nebraska to have them for 18 years. And right now, we try a fresh start. This time, for the first time, not led by physics. All the 18 years that the leadership was in physics, and everyone else was happy to follow and take advantage of the path that physics laid out. Then we also had a couple of other centers. I show them, there's more than that, but I show only what I was involved in. And these were centers that deal with spintronics, a branch that of material science that is pretty close to those quantum phenomena, because it deals with the quantum property of electrons, we call it spin, and utilizes it to make devices out of it. And we had multiple centers also, and we can also utilize the expertise we gained there. And all that together then helped, at least, I think, to write the proposal, of course, together with 20 senior PIs from 4 different campuses in Nebraska, Kearney, obviously, Lincoln, Omaha, and Creighton. And we got fortunate to get funding. This is an EBSCO center, so we got funding $20 million over 5 years. And believe it or not, I can't hardly believe it, but the first year report is already due, and I'm already overdue. I need to deliver, actually. I had to deliver today, but it won't happen. So Monday, maybe. It goes to the EBSCO center. Okay, so that's where we are. Few words about the center. Here you see Jeremy in what we call the Focus Research Group 3. So the entire center, these are all the senior investigators, of course. They all come with their own group, with grad students and postdocs and so forth. But these are the senior investigators, and the entire center is organized in what we call Focused Research Group, 3 of them, FRG1, FRG2, and 3. And I will talk more about these components that make up the center. So the Focus Research Group 1, at the bottom here of this pyramid, deals with quantum materials. So quantum materials, or materials in general, as the foundation of everything you can then build on, and then can start to think about technologies that use new types of materials. And that's what we look at in FRG2. We look into quantum technologies, so useful devices and things you can do utilizing those new types of materials in particular. And these focus research groups have subcategories, and in FRG2 in particular, we are interested in quantum sensing, metrology, and quantum communication, at least making contributions to these fields. And then finally, in FRG3, literally the pinnacle of this pyramid, there we think of quantum information processing, both experimentally and theoretically. Jeremy theoretically, but others also experimentally. Jonathan Rubel, for example, the FRG3 leader, does some Bose-Einstein condensates I talk a little bit about later. The goal there is to get closer to what we call, if you like, an analog quantum computer, so quantum emulation. But we also think about how we can contribute to the field of quantum computation, including novel ideas to realize quantum bits that are the foundation of this quantum information processing devices. Okay, so that's in a nutshell how this center is organized, and we will learn a little bit about all these different components in the last part of this presentation. Before, I would like to go more basic and fundamental things, and first want to point out again the connection, the important connection, the profound connection, I would argue, between materials and technologies. And I think one can make the case that all technology depends on materials. That's almost obvious, because all technology is made out of stuff, right? And that is better materials. So that's obvious on one hand. But one can go further, and one can argue that all progress, significant progress in technologies, almost always because of progress in material science. And I want to make the case for that. So just by looking what happened in the past and the history of humankind, if you like, And let's start when we just crawl out of the caves or something like this, the Stone Age, literally. And so they probably were smaller than we think, but that's the material they had, stone, flintstone, for example. And they could already make important devices with that. This one here, this tip of a spear, for example, is an important technology that gives this early humans, so to say, the edge. I mean, in hunting, and then of course they have meat and they can develop possibly even larger brains and so forth. That was an important first step. The next step is when, of course, it's very rough, but we may argue the next step is when we enter the age of metallurgy, and that started with the Bronze Age, an alloy actually between copper and tin. And of course, you can shape it in different forms, far more sophisticated than you can work with stone. And here's an example. This is well, if you would polish it, this would be a mirror, an early mirror made out of bronze. You can also make other alloys, brass, for example, if you mix copper with zinc. Okay, then the next big step is if you make, of course, humans always make weapons to some extent, and that's sadly enough the mother of progress very often. And the next big step to make better weapon, knives with sharper edges, is to have a harder material. And that was another big step when we entered the Iron Age. And you can have then literally an edge over your competitors. And now we slowly come to more modern times. Another big step is when we learned basically the thermodynamics of iron and how the phase diagram, if you like, of iron and carbon works and looks like, and that brought us steel. And suddenly we have a material that allows us to build new kinds of constructions. Here's this suspension bridge, for example, that utilizes the enormous increase in strength of steel. Okay, so far so good. Now again, something very profound happens. Some may argue we go from Homo sapiens to Homo informaticus or something like this. We enter the age of information by a new material. That material is certainly silicon. And you all know what happened then, literally an explosion in the sense of an exponential acceleration of return. That's a term often used by Ray Kurzweil. I like pretty much what he has to say, and he likes to make this predictions into the future, these extrapolations into the future. And he does that on solid ground to some extent, just by following the history. And here is one of his graphs, already a little bit outdated, but the trend is still ongoing. So it is the idea of if you have better tools, better machines, so to say, you make better information technology, which makes better tools, which makes better information technology, and so forth. And that gives rise to this exponential growth, or Moore's law, as we have seen it over many decades. And so here it is, you can plot it in various forms, but here it's plotted in terms of calculation per second per $1,000. It takes into account also that computers and chips get cheaper over time, and see how things evolve. And one interesting point that is basically at the heart of what people like Ray Kurzweil always like to point out is that we as humans don't have a good sense for this exponential growth. We just can't really grasp what that means. And an example for that is that pretty much the time span between a point where we make machines that do as many flops as the brain of a mouse does, and the time span go to a human, that they are identical. And but what is really mind-boggling then is if you have a computer that reaches, let's say, the processing capacity of a human brain, then it takes, again, only the same amount of time to go from the mouse to the human until you go from the human to the intellectual capacity of all humans combined. Now, that's, of course, a wild extrapolation, but so far this seems to hold. And let me point out, and we come to this in a second, the exaflop machines are there. And one is right now built in the US and a national lab. There are already some in China. And why is the exaflop scale so exciting? Because an estimate says that it's exactly the power of the human brain. It's 10 to the power 18 floating points operations per second. We are there. Okay. So that a lot has happened, right? And all that was driven by materials. And the point I want to make, of course, today is we make a next step. So we made already the step into the nanomaterials. Obviously, that's why centers like NCNM exist. But now we go a step further. Something new is happening. And the point being here that this will be the quantum materials we want to talk about a little bit more today. So the first thing I have to do is basically, again, a historic view on quantum materials. And the question that often rightfully pops up is the following. Let's say you have a physics background, for example, then this is even more so a pressing question that you say, this is all hype. What's this about? Right? We all know that the ultimate fundamental laws of nature are quantum laws. And of course, matter obeys quantum laws. What else, right? So in that sense, all matter always is fundamentally quantum. So what do you mean by quantum materials? What is new about this, right? And that's a question that often pops up. It's a valid question, but I want to make the case that there's a point in talking about quantum materials and discriminate them from other materials, such as silicon we so far had so much success. So let me come back, therefore, to discriminate what we call the first quantum revolution from the second quantum revolution, which is where the quantum materials fall. A reminder to the first quantum revolution, and I'm sorry for diversity, equity, and inclusion issues here, but at the time, this was these gentlemen that drove the field, Wolfgang Pauli, Arnold Sommerfeld, Felix Bloch, and Lev Landau. And others, of course, but they were very instrumental to basically apply, I think at the time, new quantum theory to solids. In particular, Arnold Sommerfeld was one of the first to make a very simple model we talk about a little bit later. And one of the fundamental insights in quantum mechanics was certainly the fact that there is something like the wave-particle dualism, so that, for example, electrons have wave properties and photons have properties of particles, photoelectric effect. With Einstein, the Nobel Prize, for example. But often it is of interest for us to remember that electrons have wave properties, which also gives rise to the fact that we call quantum mechanics often wave mechanics. These are very strange waves, and these wave functions themselves have no direct physical meaning. It's only the absolute square of the wave function that gives us a probability density according to what we call Born's rule. Nevertheless, waves are involved. Now, when people applied these kind of insights early to condensed matter systems, at first one would argue this is a hopeless problem. We were fortunate somehow that nature gave us the hydrogen atom, right? So we could understand quantum mechanics on the basis of the hydrogen atom. We saw the discrete lines, emission lines of hydrogen, and that allowed us to develop a theory which was basically a single particle theory. So you have a proton and an electron. The proton is very heavy, doesn't do much, and the electron is moving in the potential of that proton. And there was a one particle problem, completely new, difficult enough, but solvable, analytically solvable. Right? And then come the other elements, and things quickly get very complicated. And as soon as you have 3 electrons, it's getting really almost impossible to solve. And here comes condensed matter physics or solid state physics, however you want to call it, a macroscopic piece of matter where you have a grammar of something or so. So you have at least 10 to the power 23 or more particles and atoms. And let's say each atom contributes at the bare minimum one electron that is shared in the bonding, so to say. Then you have a problem of 10 to the power 23 electrons, not just 1, not just 2, just 3. So one would expect this is completely unsolvable, difficult. But it turns out it's just the opposite. It's in many cases, it's effectively turning again into a single particle problem of virtually independent, nearly free particles. That was another gift of nature somehow. And up to recently, this is pretty much all we could do to some extent. Let me be a little bit clear about what I mean. Let's have a look at a decent metal, a good metal actually, gold. Here, so let's look at it closer and closer. And by that point, we need an electron microscope. And then we can in fact see individual atoms. And of course, this is kind of a cartoon. So we see here the ionic cores and the potential they create, but these potentials are shielded, almost completely shielded by the electrons, the outer electrons of the atoms. And now it turns out that in such a smeared out situation, sometimes people call it a gallium or a gallium model, where you smear out the charges of the positive and ions and the negative charges of the electrons and equal them pretty much out. The electron motion in the effective potential is as if it is allowed to talk about an electron, one electron that is moving independently of all the others in an effective background potential that has almost no corrugation. So here's an oversimplified picture. How we allowed to see that. And in this picture, we could understand a lot. I want to go a little bit more into the actual description of this picture because it is really the foundation of everything we have here. That's it, this picture. Let me start by looking simply at the description of a classical free particle, a particle that is just moving without being feeling any force or moving in a constant potential, no gradient of the potential whatsoever. Then it's classically simply moving and has nothing else but kinetic energy. If you are non-relativistic, we just say 1/2 m times speed or velocity squared. We can also, and that's what theorists like more, we can express that in terms of the momentum of the particle. The momentum and the velocity are related. Again, classically, momentum is mass times velocity. So we can simply substitute that here and get this equivalent expression that the kinetic energy is momentum squared over 2 times the mass of the electron or of whatever particle is moving around. Let's plot this as a function of momentum p, right? Then we get a parabola, this squared behavior, p squared behavior. Okay, so far so good. Now comes a quantum step. So we move from a classical freely moving particle to a quantum particle that is moving without feeling the presence of a force. All we need to do, it's a big discovery, but once the discovery is made, we simply plug it in. It goes back to Louis de Broglie, who realized that because there's this particle wave duality, you can have on one side, so to say, the particle aspect, the momentum, and on the other side of the equation, we have a wave aspect, the wavelength. So he found that the momentum is related to Planck's constant over the wavelength. And you can, again, for some reason, the theorists always must find a way to write it more fancy. They like to write it as h bar, which is the exact same number divided by 2 pi. And then they multiply it by a wave number they call k, which is 1 over the wavelength, but multiplied by 2 pi to correct for this 2 pi again. Anyway, it's the same thing. The Broglie relation connects P, the momentum particle property, with the wave property, which is the wave number k. We plug it in here, and again, can plot it as a function of k and get again the quadratic relation. And it looks the exact same thing. It's a parabola. Why is that interesting? Because that brings us almost immediately to what is known as the band structure of solids. And the band structure of solids explains everything we know quantum mechanically about materials as we know them. Metals, why are there metals? Why are some materials semiconductors? Why are other materials insulators? All that can be understood in terms of the band structure of solids. And the band structure of solids looks like this. And notice, you rediscover the parabolas of the free moving particles. The only thing that is different here is that there's a gap. And this gap comes from the fact that this effective potential these particles see, the electrons see in which they move, is not really fully smeared out and fully flat, but has some corrugation left. And it is that amount of corrugation, the more corrugation there is, the bigger is this band gap. And a band gap then determines, let's say, if this part is occupied with states and the upper parts are not, and the band gap is big enough, then you have an insulator. If the electrons are only occupying a part, a fraction here in the bottom, you have a nice metal. If the band gap is small compared to energies that are provided by thermal excitations of the environment we live in, long sentence, if the energy is small or comparable to K Boltzmann times temperature, then we would call that thing a semiconductor, because then you can have thermal excitation. And despite the fact that there is a band gap, you can still have conduction. So that tells you another thing, by the way, just from this. Whether you call something an insulator or a semiconductor depends on, let's say, on what planet you live, right? If you live on a planet that is very hot, you would probably call what we call an insulator, you would call a semiconductor, and so forth. Okay, so this explains everything we have done so far. And now I show you the technologies we get out of this. Really, I'm not making this up. This understanding gave rise to the understanding of semiconductors. Understanding semiconductors and later doped semiconductors allowed us to build transistors. And once we had transistors, we made transistors just better. That's it. Okay, we made a step from a bipolar to a field effect transistor, but still, it's all that, nothing else. And that gives rise to wonders and miracles like this. This is the exascale supercomputer that is supposed to be present in 2023 at the Lawrence Livermore National Lab. As I said, this is remarkable because the computational power is probably even bigger than that of a human brain already. An unfair comparison, because I think you need almost an entire power plant to power this thing, and we just need a few watts. That's a big advantage of the brain. And that's where a lot of research is going in today, to make devices more energy efficient. We have cell phones, of course. You can talk about the wonders of a cell phone. It's just a miracle that we have these computational powers and whatnot in our pockets. Unbelievable. We have lasers, and in a sense, also lasers can be understood, solid state lasers can be understood in these terms. And even the conventional theory of superconductors, which we use for nuclear magnetic resonance, for example, in hospitals and so forth, can be understood in the conventional single particle type picture. Here you see, by the way, a nice animation that explains nicely, but of course oversimplified, why the magic of superconductors happens in conventional superconductors. So the electrons, they pair into a new type of particle. They undergo transition from fermions to bosons, and they do that by exchanging virtual phonons that are lattice vibrations or lattice deformations that you can see. That gives rise to this pairing, and once they are bosons, they can condensate into a common state, kind of a Bose-Einstein condensate, and that is separated from the next, from excitations by a gap, and that's why you can have resistance-free conductance of current, for example. Okay, what else do we have? And now we come closer to technologies that are more modern. And I would already call them quantum technologies, of course, but they are still quantum technologies in that sense, in that quantum single particle pictures, which we fully understand. Here's one you can buy at Best Buy, a quantum dot laser. So what is quantum about these things is that these TVs, they have extremely wonderful colors. And the way they do that is they use particles, semiconductor nanoparticles. Semiconductors typically on the order of, let's say, 5 to 10 nanometers of diameter. And when you have particles of that size, then the electrons that can move in this material, they suddenly strongly feel that the particle is finite, not infinite, like a big piece of bulk material. It's finite. And this confinement of the electrons creates standing waves, solutions of the Schrödinger equation as standing waves. Here they are. And now you can have transitions between these discrete energy levels. It's very much reminiscent of atoms. Actually, we call those quantum dots also artificial atoms, because they have a discrete energy level and they can have transitions between these energy levels and emit a very characteristic wavelength of light. Now you can tune the wavelength of light by changing the size of the nanoparticle. You can see actually that in the formula for the energy levels. L is the diameter of the nanoparticle. And if you make it bigger, then the energy goes down. If you make it smaller, the energies go up. And so you can tune the energies. And I want to show you that in my first demonstration, I brought you these nanoparticles. So here in these, I don't know if you have seen it before, but here in these cuvettes here, you have nanoparticles, same type, same material in solution. The only difference is that they vary in diameter. And I want to show you that this means that if I excite now those transitions with ultraviolet light, then I excite states, electronic states up, and then the system will relax back into the ground state, and by doing so emit light. And that light depends on the energy levels and therefore depends on the size of the nanoparticles. So this is UV light, high energy photons. This is a particular color, orange, I would say. Yellowish, green, and a darker green. And again, there's no difference. Oh, for my friends, for my Zoom friends, here we see orange, yellow, a light green, and a dark green. Oh, we still don't see that. Sorry. I try to make it visible. All right. Okay, the camera has a hard time to pick up the colors. Yeah, it's difficult for the camera to distinguish, to discriminate the colors. Sorry for that, but I have more demonstrations later. Oh, way. If I go away button here. So we have seen the quantum.tv. So the quantum.tv works like this. You have these quantum dots, and you shine light from behind on the quantum dots, and then they have this characteristic emission in very brilliant colors. Okay, at some point we will have quantum.tv where you simply emit the light from actual individual quantum dots by electrical excitement. That's also going to happen. Okay, what else do we have? Another device that is still a conventional quantum device, but still very interesting. It is based on what we know as the quantum mechanical tunneling effect. I have here an animation which I have stolen somewhere. And what does this animation show us? Well, it shows us an effect that is absolutely impossible in the classical world. What we have here is a particle that is coming in from the left and traveling towards the right. And then the particle hits a barrier, a wall, or how you want to call it. You can think of it as a potential well, literally as a hill. And of course, in the classical world, if you come in with kinetic energy of a certain amount, and you have to overcome a hill that has a potential difference in energy that is more than the kinetic energy you come in with, it's not going to happen. You just bounce back. You cannot overcome it. In the quantum world, because quantum particles are also waves, that's all that creates this effect. You have a certain leak screw effect here, so the particle can actually have a finite probability of appearing on the other side where it's classically absolutely forbidden. And so you see the incoming wave package representing the particle is bouncing off the potential step here is partially reflected, but partially concealed. That's the quantum mechanical tunneling effect. It's already fascinating, but it's a single particle effect. And here's a device. I show you first the animation and then I show you the real thing again. Here's a device that utilizes this. It's a pressure sensor. Pressure sensor works like this. You have a matrix, a polymer matrix, and in that matrix you have metallic nanoparticles. And as long as you don't put pressure on this matrix, the particles are far away from each other. But as soon as you put, what did I do? Not get the second revolution. As soon as you put pressure on it, the particle gets closer to each other, and that means, so the probability of tunneling depends on two effects. It depends on the height of the barrier, and it depends on the width of the barrier. So if you bring this particles closer together, basically the width of the barrier goes dramatically down, and tunneling can set in, and that means you have conduction. And that can be used for a sensor. And guess what? I brought a sensor like this. Very rudimentary thing. So this is this polymer with the particles in it. I put it on this. Oh God, yeah, this is will be difficult, but I try my best. Okay, we can see this. So the other electric contact here. And all I have to do, so to say, I have to create an electric connection between these two copper strips. And as long as I put this material on top without pressure, this is an insulator and it's not conducting. But if I put pressure on it, it becomes conducting. And then, as a proof of that, you see that the diode is emitting light. You see that? And maybe I try again the slide. And it's very sensitive to the pressure. I can give it more pressure, and then there's more light, and less pressure, less light. Very sensitive. That's quantum mechanical tunneling. Here's the first one. Workouts here. All right. It takes a moment. All right, so we did all this. Now it's time to talk about the second quantum revolution. I got, oh no, oh God, yeah, I better start, right? So the ancient Greeks are over. Let me go back. What's the second quantum revolution in a nutshell? Well, it's the opposite of the first, right? In the first, we could talk about basically all the effects were just single particle effects. We could describe everything by effectively having one particle independently moving off the others. And in the materials of the second quantum revolution, that's no longer possible. The materials, now we use fancy words, right? We say they are strongly correlated, which means we have no idea how to calculate it. So that means the motion of one electron completely depends on where all the other electrons are. Everything affects everything. That's not too surprising. That's the nature of the electromagnetic interaction. The Coulombic interaction is like that. It's long range. It never stops. It was only because of the shielding effect that this effect was basically canceled out. But there are materials where it's not. And those materials, here's my stupid animation that tries to show this. See how they move? They all move. So one particle starts to move. Because of that, every other particle is solid as effect. For theorists, that's a nightmare, right? It is. But it is also a chance to predict completely new phenomena which we couldn't even think of, right? Because they cannot be predicted from these local interactions. Now, what is that? There's a whole zoo of things one can think about. And the most profound second quantum revolution effect, I would argue, the most visible is high TC superconductivity. It's a new form of superconductivity, not that new anymore, but it belongs into this category. These materials are oxide materials, insulators in the normal state. They're not even metals. They're insulators. And then you cool them down, and suddenly this phenomenon of Bose-Einstein condensation happens. So the spins again pair. They go from fermions, which have half-integer spin, into particles where the spins compensate. They have their integer spin, and then suddenly a new statistics applies to them, Bose-Einstein statistics. And at low enough temperatures, all the electrons can condensate into a common state. So all the electrons suddenly lose their individuality and become one big blob and become superconducting. Now, this is in a sense a poster child of the second quantum revolution, because what we also are after are quantum effects that are macroscopic. You know, everything is quantum. And if you go down to the small details, you have to use quantum mechanics. But on the macroscopic scale, we hardly ever see quantum mechanics in action. Superconductivity you see. So that's a fantastic effect, and I'll show you that in a second. Then we have so-called heavy fermions. So this looks exactly the way I showed it to you. I can again describe my electrons with these parabolas, but suddenly the electrons have a mass that is 1,000 times bigger, for example, than the mass of an actual ordinary free electron in there. And something profound happens. And many, many other effects, often related to oxides, materials where the electrons strongly interact and are localized. And fantastic effects can happen if you bring them into heterostructures. Then, by the way, we talk about emergent quantum phenomena. You create heterostructures where emergent phenomena happen at the interfaces between the material A and B. A property that is neither in A nor in B suddenly pops up at the interface. You can have oxides, bring them at interfaces and create two-dimensional electron gases, superconductivity, metallic states, all kinds of things can happen. You can have multiple heroic orders, we call it, again, a fancy word. The interesting part of this is ferroelectricity that can happen, right? So polarization that has remnants and can be switched in an electric field. You can have so-called metal insulator transitions, where a system is an insulator, you cool it, and suddenly it changes and becomes a metal, and you can change by external electric fields the carrier concentration of electrons or holes in the system, and completely change the properties by external stimulus, and many other things. In addition, when you broaden this definition, you can have what is known today as topological states of matter. That's a very exciting new keyword. Sounds fancy, and as a matter of fact, I think it is fancy. I really think it is profound. It is really new. Let me roughly show you what we mean by that, for those who don't know. First of all, let's forget about this green stuff here and look at the blue and the red bands. That is same old, same old. That's exactly the band structure as we have shown it from the single particle picture. And in this case, because you have a large gap between the valence and the conduction band, that would be an insulating material. So it's an insulator, nothing special about it. What is special about it is that this insulator can have surface states, and those surface states are shown here in green, which suddenly make the surface of this material conducting. And not only that, it creates edge currents on this material, which flow in particular directions. One flows like this, shown here, and the other one flows in the opposite direction. And locked in with this direction of current flow is the orientation of the spin of the electron, or the little magnetic moment the electron has. That if the current goes like this, the electron spin may look up. If it goes the other way around, it may look down. And this is a completely new class of materials known as topological insulators. And you can make very fancy things with that. Also relevant for quantum computers, by the way. And here, in the same context, by the way, this word topological insulators, topology, comes from mathematics and basically refers to objects that qualitatively don't change if you make small changes to it, small deformations, for example. Right? There's this stupid idea of the picture you always see of the donut that turns into a coffee mug or something like this. By continuous deformations, as long as the object has one hole and you just continuously deform it, there's a certain property, a kind of a conservation quantity, a genus, that is not changing. And that makes these systems special. It makes them, in physics, it makes them robust against perturbation. Here's another example of such a topological structure. So you can have topology in these band structures, in momentum space or in K space, we call it. But you can also have topological structures in real space in terms of spin textures. And this thing here is such a topological structure in spin space. It's called a skyrmion. And the thing about this is it's a little bubble, which you can, for example, use to store information. And this bubble is very stable. That's the good thing about it. So it is robust against breaking up. So useful. Okay, so all this is matter of the second quantum revolution. Finally, I come to what is EQUATE doing. And I come to the research group 1. This is the group of people who do not do the work, right? Those who do the work, I don't show. I don't even talk about it. Okay. So what are we doing here? We do quantum materials. And I give you just a few examples of what we are doing. It gives you just an idea. So this you have just seen, right? This is such a spin structure, this fancy spin structure called skyrmion. And now you can do all kinds of things with them. For example, you can drive an electron current through the material that hosts the skyrmions. And then it turns out that the electrons feel an effective magnetic field because of the structure and bends the direction in which the charge is flowing. And that you can use to create a transistor. If you, for example, by strain, here this is a PZT piece of material, so it's a piezoelectric material. If you apply an electric field, this deforms and strains this. If you strain it, you can affect the structure of the skyrmion, and by affecting the structure of the skyrmion, you can affect the way how the electric current is flowing and build a transistor, a new type of transistor. For some reason, we always build transistors. Yeah, because I think they are pretty useful. Okay, and here's another example again from topology. The system is in a particular magnetic order, and the magnetic order, interestingly enough, ties to the electronic structure. So if you change the magnetic order, in this case, we change the orientation of all spins. Those that pointed up, we let them point down. If you change the magnetic order, you change the electronic structure and you open a gap here. And again, what do? You build a transistor. Perfect. Build a transistor. Another example, more theoretically inclined, is here. We look at these nasty things. Finally, we look at them and we try to develop methods to actually deal with that. The fact that the electrons are no longer independent of each other, but see each other strongly, gives rise to correlations. And these correlations have effects which we haven't thought about so far. And this affects a lot of things, and this is the way to theoretically study those correlations. Now we get closer to what I do. Actually, this is an image that has been created in my group. It's a particular material called chromium oxide. This material is magnoelectric, very exciting. I'm excited about this. And because I'm applying electric fields to that material, an electric field. And by applying an electric field, you create magnetization in the material. That's fairly unusual. It requires particular symmetry requirements. And it is one of those oxide materials that fall into the class of quantum materials. Now you can go one step further and put graphene on top, this fancy material that is just one layer of atoms. And then you can let interact the spins at the surface of this chromium oxide with the electrons in the graphene and build a transistor. and here is kind of a step in the transistor. This actually worked for my group, recently published. Here we have, again, this material chromium oxide. This, by the way, is a real image taken from the lithography we do at the Nebraska Center for Materials and Nanoscience. And this is an example how you can electrically switch the structure here of these spins. You switch them from up, down, to down, up. And when you do so, you can drive a current here through a Hall cross, measure a particular voltage, and this voltage switches. It switches in a non-volatile way, and that is very useful. Believe it or not, this is almost the holy grail of memory, because now we can, without magnetic fields and without electric current, we can just by voltage, without joule dissipation and energy losses and all this ugly energy consumption of the electronic devices we have so far, we can switch between different states. That is really useful. Yeah, we recently published this. And of course, we want to build the foundation for new type of qubits. Oh, I see the chairperson looking at the clock. No. And so let me first say a word about qubits. Not everyone is supposed to know immediately what a qubit is, right? So again, this is an interesting subject. We can only touch it here. We should start with the classical bit, right? So you can have a bit that can store information. I'm coming from magnetism, so let me talk about the magnetic bit. And in the magnetic bit, the magnetization can point up or down. If it points up, let's say it stores information 1. If it points down, it's 0. In a qubit, you can utilize the incredible fundamental property of quantum mechanics that you can, that different ways of looking at it, that you can, oh my God, I didn't show the high. I must show the high. Anyway, let me finish this. In quantum mechanics, you can build superpositions. So you can have a system in a state where the spin is not only pointing up or down, it is in a linear superposition of pointing up and down at the same time. Right? So that is the foundation of quantum parallel behavior, because you can now process these qubits by quantum gates, for example, and you process more or less instantaneously both states rather than just one at a time. Now you can bring this to an extreme, and that is what quantum computing ultimately is really about. You can take multiple qubits, ideally a lot of them, and bring them into another very exciting, very exotic superposition state, which we call entangled states. And then you can have, so to say, let's say you have a computer with 100 bits, right? And if the computer is in a particular state, that means the 100 bits are, each of them is either up or down, or up or down. And at a particular moment in time, there's a particular configuration of all the bits. Fine. And there's another moment, there's another configuration. In a quantum computer, you can have a system at a particular moment in time in a linear superposition of all states that there are. And then you can operate on this state. And of course, you have an enormous exponential gain in speed up for some very special problems. One of this is the infamous Shor algorithm that can, for example, factorize large numbers into primes. Okay, so we are interested, everyone is interested in realizing qubits. Currently, the favorite qubits are superconducting circuits. Show you superconductivity in a minute. We want to go another route, not just we, but we also want to go a route that allows us to create qubits in this metal-organic frameworks. So where we have spins sitting here in this environment, more or less shielded from the environment, so that you can keep this superposition state as long as possible. But we want also to link and let them interact so that we can create these states of entanglement. And for that, you need these linkers, again, spins that can switch on and off interaction between the individual qubits. So that's something that's also investigated in group 1. Okay, before I move on to group 2, I must go back and show you, of course, this. I mean, come on, I brought it all the way. I even brought liquid nitrogen. And yeah, scary. Somewhat. Okay, so for my friends online, if there is still any left, I don't know. Oh God, no, my mouse is doing this again. Oh. Okay. Hide. Do this. Okay. So what do I have here? This is really a second quantum revolution material. It's an ITC superconductor. And the reason that it's ITC is I can bring it into the superconducting state by cooling it just in liquid nitrogen, 70 Kelvin or something like this. That's a high temperature for, and that's amazing. And then I show you the properties of this type of superconductors in general, which are also amazing, because this is a macroscopic quantum phenomenon. So you see something that can only be explained by quantum mechanics on a macroscopic scale that is very rare. Let's grab some nitrogen here. Or maybe I do this here. I dip this material. I don't know, it could be yttrium, barium, copper oxide, or something like this, one of these high TC superconductors. I dump it in here and let it boil for a minute. Meanwhile, we enjoy the Leidenspost phenomenon a little bit. Okay, so I used the time to explain what will happen. So when the superconductor is in the superconducting state, it has two properties that make it a superconductor. One is the obvious. It can carry electric current without resistance. But if you really want to test, if you don't have just another form of an extremely good conductor, or if you have a superconductor, you need to test another effect, which is known as the Meissner-Ochsenfeld effect. And that is that the superconductor does not allow to have magnetic field lines in it. It pushes them to the outside. And that effect, if you now take the superconductor when it is superconducting and bring it into a field, then it pushes the field lines away, and that effect can create a force that counteracts gravity. So I can make this piece of material levitating in the presence of gravitational field. That's one effect, but there's a special type of superconductors, this one here, that don't do that perfectly. They allow for flux, magnetic field lines, to penetrate through the material, but only in units of flux quanta. And those flux quanta go to particular places where the superconductor is not so perfect, at defects, and want to stay there. It's energetically favorable to be there. And that gives rise to a phenomenon known as flux spinning. And this is why this magnetic levitation can work when everything works fine. So I can take the superconductor, let it levitate on this array of magnets, but put it into a circle and let it float around. Let's see if it works. Without, oh God, I try. Okay, not so bad. See that? Isn't that unbelievable? I do that one more time, simply because a bit of effort, and it was not bad, but maybe you can get it a little bit more convincing. But you saw the effect. It's floating, it's levitating, and that is the effect, that is the Meissner-Ochsenfeld effect. And then the fact that it's going in a curve means otherwise, I mean, Newton's law would say go straight, right? So there's a force, and to be able to not fall off, you need to have this flux spinning effect, which is the effect of this particular type of superconductors. That's why one should wear glasses and gloves. That's not so bad. Okay. No. One more time. It's a fine line. The thing is, it gets too quickly too warm. It should have a reservoir, but it does. Okay. Here we go. Oh, and then it gets warm, and when it's really warm, it sinks down. Whoop. All right. Did you see it, or did I block it? Anyway, good. That's all we got. Well, that's also fun. All right. Okay. Okay. Back to our stuff. We have done this. Yeah, we go to FRG2, and I come to an end at some point. Okay, so this is the investigators of FRG2. FRG2 is about, maybe you're more interested in that, maybe it's about quantum technology. So what can you do with these new types of things? And a couple of things we can do are quantum sensors and quantum communication. And let me first say a word about quantum sensing and how it works, why it works, very, very briefly. The rough idea is, we have seen from the qubit that the essence of quantum mechanics is superposition and entanglement to some extent. So you can have superposition. But this superposition is rarely observed in the real, in the macroscopic world we live in. That is because of an effect of decoherence. So these systems, quantum systems, are very sensitive to decoherence. That is basically interaction with the environment or external perturbation. That's a problem for quantum computing for sure. But it can also be considered to be a strength if you want to be sensitive to external perturbations. And that's kind of why quantum systems can be useful for sensing. And quantum communication, of course, that is that everyone's excited about that, particularly about quantum cryptography. We all know, if we make transactions with our credit cards or whatever, or if the Department of Defense has some security issues, we don't want necessarily that someone else could hack into our transmission of our data. And with quantum cryptography, there seems to be a way to achieve just that. Namely, that you can either, for sure, figure out, at least if someone listened in, that's not too bad, right? Or you can completely, in the future, maybe avoid that with a concept known as quantum teleportation. So these are interesting aspects, and we make our contributions. Let me start with sensing. We use, among other things, we use these systems called nitrogen vacancies. So what is that? So basically, you have a fancy type of microscope. These days, commercially available, you have so-called scanning probe microscopes, atomic force microscopes, one of these, where you have a cantilever with a very fine tip, atomically sharp, and you scan it across the surface of a piece of matter, and you detect the interaction forces between the tip and the atoms on the surface. You can detect that by detecting the bending of the cantilever, basically. That is an AFM, an atomic force microscope. Now you can put on that tip a particular defect, and we call that a nitrogen vacancy. What is that? You have a diamond single crystal, and you make a defect in such a way that you replace one carbon atom by nitrogen and remove a nearby carbon atom and create a lattice, a void spot in the lattice. Now the nitrogen, if you look in the periodic table of elements, nitrogen is just next to the right, it has one more electron. It can give off one electron and donate it, so to say, into the vacancy and create there a very similar situation as we had for this quantum dot situation where we had a particle in a box. It's basically, again, a particle in the box problem. This time, the particle can have a spin, and you can have the spin being in different orientations, in different states. And the energy difference between these states is very sensitive to external perturbation, for example, to external magnetic fields. So long story short, you can extremely sensitively measure magnetic fields with these nitrogen vacancies. And by extremely sensitive, I mean, you could, for example, measure from the outside the currents, the magnetic fields that the currents create that happen when your brain cells fire. It's these type of tiny currents create magnetic fields which you can easily measure. So this is very useful, and it's useful in material science as well. We are interested in that as well. Actually, I collaborate with them on this material I just showed this guy here. Now, you can do more. You can also do fundamental quantum physics of the second type, if you like. You can take more than one nitrogen vacancy, more than one of those spins. This is a qubit, this is a qubit, and now you let them control, interact with each other and create an entangled state between the qubits. Something like this. This is a highly non-trivial state between two qubits, an entangled state, which has a property like this. You know everything you can know about the entire system by writing down this wave function, but you know nothing, absolutely nothing about the individual constituents. It's just the opposite of what we are used to in our world, right? We always think if we know something about the constituents, then we know everything about the system. It's just the opposite. The entire information about the system is distributed in correlation. It's a very bizarre phenomenon. If you heard about spooky action at the distance, that's where this stuff comes in. Remember, spooky action at a distance doesn't exist. It was the wrong way of thinking of Einstein about this problem of correlation as we think today. Anyway, these are very exotic systems, very important for quantum computation, and we try to study those as well. Then you can do other things. You can also create a new type of magnetic resonance imaging with an advantage that you don't need this extremely large magnetic fields anymore. So if you get an MRI these days, they put you into this tube and create multiple Teslas of magnetic fields to get a contrast. And there are ways, again, that utilize nitrogen vacancies to get away with extremely small fields. That's useful. And last but not least, there's, of course, quantum communication. And entangled systems, but better for communication, entangled photons, so packages of electromagnetic waves, if you like, are an ideal way of communicating information across long distances. Photons, we call them flying qubits, and there are ways to create entangled qubits by a process that is known as down conversion. So paramagnetic down conversion. So you come in with an electromagnetic wave of one particular frequency, and then you emit two photons of half of that frequency, so energy is conserved. But these two photons, because they were born at the same time, at the same point, they are entangled. And this entanglement, this correlation between them never goes away, no matter how far away they are. If you send one to Andromeda and you measure this one, instantaneously this one is affected by this. This is the property of entanglement. Very useful for quantum communication. And I guess, no, we have one more. Oh my goodness, I almost forgot Jeremy. So. 3, FRG3. That is the pinnacle of this pyramid, the most difficult of all tasks. But let me, of course, the reward is also the highest. What can you do if you can do quantum computation, right? So you can do all kinds of promising things. You can look for new drugs, catalysts, new materials, new types of GPS-free navigation. All that is possible if you once have quantum computation. Now, the first step towards general quantum computation is something that is analog quantum computation, if you like, quantum simulation or emulation. And that is done experimentally done by folks like Jonathan Rubel, for example. And he creates Bose-Einstein condensate. Literally in the big lab experiment in ion traps, he uses potassium ions to trap them and then let them interact in controlled ways with very low temperatures, and then the magic happens again. The individual atoms lose their identity and condensate into a single quantum state where they are just one. You cannot distinguish anymore properties of individual atoms. Now, what you can do with these things is you can create the interaction between the atoms in a very particular way that they describe another physical condensed matter system, for example. And then you can let the quantum mechanics do its magic and let the system come to its ground state. And then you look, what is the ground state? And if you do that, then you have solved the quantum mechanical theoretical problem. You found the ground state of a particular problem, of a particular Hamilton operator. That's very interesting. And that can be done already. That can be done in this complicated ultra-cold atom experiments, but we can also do it in very exciting new ways, in very cheap, very simple, in condensed matter systems, where we have a new type of quasi-particle, exciton, polariton, doesn't really matter what that is, but it's another bosonic particle that again can condensate into such a Bose-Einstein condensation, which you can then use to emulate certain problems, find ground states of certain Hamiltonians, for example. And that's also where Jeremy comes in, and he's interested in a particular class in the theory of polarons in something rather complicated, in this dipolar and spinor glasses. So whenever you hear dipolar, that means you have dipolar interactions, and that's another beast, because that's another of these long-range interactions, which is so nasty, because everything here depends on everything everywhere else. Difficult problems. But of course, the reward is big. Quantum walk algorithms is again like quantum versions of search engines, allows you to find certain optimized pathways and search structures. And last but not least, we have a theoretical attempt to create a particular type of qubits by these quantum cross wires. And these qubits, these are not spin qubits, these are electronic qubits, and they may have a possibility to create quantum computing at higher temperatures. So because of energy differences between ground and excited states being higher than in spin systems, you can cope with more thermal excitation before decoherence sets in. And that can be useful to bring quantum computers away from where they are currently at IBM, Google, Honeywell, or elsewhere, at ultra low millikelvin temperatures, and bring it hopefully more to something like this. Well, that's far away, but that would be the ultimate goal. If you can run a quantum computer, let's say at liquid nitrogen, that would be great. Okay, believe it or not, I'm almost done. If you didn't like a word of what I said, that's okay. You can still listen to this video, which summarizes it in better words. It's a bit hyped, but it's a nice summary of what EQUATE is doing. It's 1 minute, and so let's try to listen to this. But I don't have audio, huh? Why do I have not audio? Okay, let me try that again. Okay, then you know what? I do not show you the video because it's basically in 2 minutes what I said in way too much time. So then let me thank you for your attention, and let me also thank the sponsors. That, of course, is very important. All right, I'm happy for questions, if there are any. Forever battery? Yeah, okay. Right, yeah. I mean, there are multiple attempts. One interesting development is the supercapacitor, for example, in this context. We in this center, we don't work on this. Can do all, but it's related to some extent to the superconductors, the supercapacitors, but also the virtually all types of modern